Chapter 14 is on antimicrobial therapy. Usually, we use the term antibiotics, and so you will probably hear me throughout this chapter use antimicrobial therapy and antibiotics interchangeably. So, like most of these chapters, we start off with definitions. So, the first definition we talked about early on, chemotherapy. We usually think about cancer and really strong toxic drugs when we think about chemotherapy. Chemotherapy is really any chemical agent that's used to treat any aspect of a disease. Antimicrobial therapy, this is a chemical that's used to treat diseases that's caused by microbes. Now, the true definition of an antibiotic, this is a chemical substance which is produced by microorganisms that has the capacity to inhibit the growth of bacteria. If you remember learning about Fleming, he was working with bacteria and he noticed that there was a fungus on his plates and it was actually killing the bacteria. That is the true definition of an antibiotic, but we tend to use them interchangeably. If let's say that you have strep throat and you go to the doctor and you get a prescription to help treat it, we usually don't say, "Oh, I went to the doctor and they prescribed an antimicrobial therapy." We usually say, "Oh, I went to the doctor and they prescribed an antibiotic." So again, we tend to use these interchangeably. Many of these antimicrobial therapies can be synthetic drugs. So these are going to be chemical agents that are produced in the lab. Many of them can also be semi-synthetic drugs. So we start with a chemical precursor that's made in a lab, and then we can give it to a microorganism that can do some chemistry on it that we normally can't do in a lab. And then that microorganism can actually complete the synthesis. So we can do this on a very large scale. So when scientists are designing antibiotics or antimicrobial therapy, one thing that they take in mind is toxicity. You certainly don't want to give a drug to somebody and have that drug make them sicker than the microbe. So, toxicity really has to do with dose, exposure, and metabolism. I think there's a myth out there that all natural products are non toxic and chemicals made in a lab are always toxic. Everything is toxic. It just depends on that dose, exposure, and that metabolism. Just because something says that it's non-toxic and it's natural doesn't mean that you can spread it on a cracker and eat it. I often use the example of alcohol when I'm talking about dose, exposure, and metabolism. So let's imagine that you went to a party and you had a cocktail and you drank that cocktail over 4 hours. So that dose is not going to be that strong because it was a little bit over 4 hours. The exposure is how you got it into your system. So you drank it. So that was ingested. Your metabolism is your body's way of getting rid of it, especially with the liver. So, how is your liver metabolizing it? Now, if you had a cocktail over 4 hours, that dose, the metabolism is going to be able to break down that dose. The exposure, you're ingesting it. Now, imagine that you went to the same party, but you had 3 cocktails in an hour. So now the dose has increased. The exposure is still the same. So you're ingesting it, but now your metabolism is overwhelmed. So now you're feeling those toxic effects of alcohol, which is why some people, let's be honest, will actually have a few cocktails, right? Now, if you, let's say, were to take a bath in alcohol, I don't know why you would do that. It would be very expensive, also very drying to the skin. The dose is certainly going to be huge. Exposure is going to be a little different. So it's not like you're ingesting it. You would actually be sitting in it. So it would actually have to go through your skin. Because your body really isn't getting that exposure, your metabolism isn't going to be overwhelmed. So when scientists are developing drugs, they keep toxicity in mind. And what they're trying to do is they are trying to design drugs with selective toxicity. So we want to harm the pest, we want to harm the microbe, but we don't want to harm the host. It's the same thing when they're designing pesticides. So if you're buying an ant spray or a roach spray, you want to make sure that it's going to kill that pest, but it's not going to harm you or your family or your pets. So, this is what scientists keep in mind when they're designing antimicrobial therapy. Now, every drug is going to have variable ranges. And what we want to do when we're prescribing is to make sure that we're hitting that therapeutic dose level. This is going to be the dose level where it's actually doing its job. And we don't want to give too much where it's actually at that toxic dose level. So when they're prescribing drugs, we want to make sure that we're at that therapeutic dosage level. So that way we're going to optimize the use of that drug. Now, usually when people are prescribed drugs, oftentimes, especially if they're getting IVs in the hospital, sometimes they can actually test to find out if they are actually getting the correct dose and it's doing its job. Usually, these things are also done by weight as well, because we want to make sure that we are getting the correct dosage in so that it's at that therapeutic dosage level so that it's actually doing its job. So, if we take a look at different antibiotics, there's actually a spectrum of antibiotic activity. Some are going to be very specific for certain types of bacteria. Some will actually be a broad based antibiotic. If you take a look at the tetracyclines, and that line is towards the bottom, it actually hits a wide array of bacteria. So, this is what we would term a broad spectrum antibiotic. So, if a clinician wanted to cover all bases because they weren't exactly sure what pathogen was causing the illness, they might use a broad based. If they know have a pretty good idea, and sometimes they're actually able to do some tests to find out exactly what the causative agent is, but sometimes they can kind of take a best guess and know which antibiotics are going to hit those particular organisms. One of the things that you will hear me talk about is that it doesn't seem to be summer in my house unless one of us gets cellulitis. And I've ended up with cellulitis a couple of times, maybe from a scratch, most likely from a bug bite. So, one of the times that I had cellulitis, when I went to the doctor, they said, well, we've got a lot of staph and strep on us. So, it's more than likely that one of those organisms entered in either through a microabrasion, a scratch, or a bug bite. And so the clinician said, let's target something that's going to hit those gram positive bacteria. So that's the type of antibiotic that I was prescribed. If you take a look at the mycobacteria, remember these are things like leprosy and tuberculosis. There's not a lot that will actually hit it. They actually can be pretty toxic. So in those cases, it's probably going to be a pretty toxic drug and taken at a long interval. So a lot of times clinicians will kind of do their best guess. Sometimes they're lucky enough to know what that culprit is. Sometimes knowing where the infection is, the mode of entry, they can kind of take their best guess so that they know which antibiotics are going to target which pathogen. So let's take a look at how antibiotics, antimicrobial therapies work. So some of our first antibiotics actually worked by inhibiting how the bacteria make that cell wall. So early on, we talked about how bacteria, they have a unique cell wall. They have that peptidoglycan. We do not have that peptidoglycan. So antibiotics that target peptidoglycan, it's going to be selectively toxic because it's going to harm the bacteria. It's not going to harm our cells. So these particular drugs that inhibit cell wall synthesis, these are beta-lactam ring antibiotics. And I've got a little picture where you can see that beta-lactam ring. These beta lactam rings interfere with the enzymes that actually help to form that peptidoglycan layer. So it's going to target that bacteria. It's not able to make that cell wall, it's not able to make its fence. That means it's going to be vulnerable and it's not going to be able to live. This is an example of being selectively toxic because it's not going to harm our eukaryotic cells because we have peptidoglycan. So some of our first drugs, so things like penicillin, cephalosporin, amoxicillin, they work by using these beta lactam rings. Some antibiotics will interfere with cell membrane function. So the polymyxins, they will work on bacteria, especially gram-negative bacteria. If you remember gram-negative bacteria, they have kind of like that peptidoglycan sandwich where they have the inner membrane, thin layer of peptidoglycan, and then the outer membrane. So they will actually work on that membrane. There are some that will actually work on fungal cells that won't affect our cells because those fungal cells are going to have some things that are different than our eukaryotic cells. Some antibiotics will work by inhibiting protein synthesis. We call these aminoglycosides. So things like streptomycin, erythromycin, tobramycin, they're going to work on how the bacteria makes proteins. If a bacteria can't make proteins, bye-bye bacteria. It's not going to be able to live. So if you remember the ribosomes, when we talked about protein synthesis, bacteria have 70 S ribosomes. Our eukaryotic cells have 80 S ribosomes. Their enzymes are also going to be a little different than ours. So these types of drugs are going to target how bacteria make proteins by either affecting the ribosomes or affecting the enzymes that actually help to build those proteins. Some antibiotics will inhibit nucleic acid synthesis, so interfere with how the bacteria can make its polymerases, so DNA polymerase or RNA polymerase. Some will actually inhibit enzymes, so they will be these anti-metabolites where they will actually attach to an enzyme so that a substrate can't bind to it. Then that enzyme isn't going to be able to do its job and that bacteria isn't going to be able to carry out its metabolism. Sulfa drugs tend to work by being anti-metabolites. We talked about in the viral chapter that antibiotics are not going to affect viruses. And this is why. Viruses do not have that peptidoglycan layer. Viruses do not have membranes. Viruses are not going to undergo metabolism. So when we're making antiviral drugs, we tend to use molecular mimicry. So I brought in a little picture from chapter 11 in viruses, and we talked about adsorption. So how that virus can adsorb to the cell by either the canyons and those capsomeres binding to receptor proteins on the cell, or by those spike proteins binding to receptors on the cell. If we designed antiviral drugs to tie up those binding sites, then it's almost like keeping that virus in a little bubble so it can adsorb to the cell. So that's how many of our antivirals work. So if you have the flu, taking an antiviral can help with that. If you end up with a secondary bacterial infection because of the flu virus, then it's going to be appropriate to take an antibiotic. So if you're a visual person, this is a little picture that just kind of shows how each of these antibiotics are targeting the bacterial cell. So number one, we talked about that cell wall synthesis, interfering with that peptidoglycan layer. So things like penicillin, vancomycin. Some will disrupt cell membrane function. Some will be those aminoglycosides, so interfering with protein synthesis, like erythromycin, streptomycin. Some will inhibit nucleic acid synthesis, so the ability to replicate that DNA. And some will stop or slow down metabolism by acting as those anti-metabolites, like those sulfa drugs. So in lab, we will actually have the opportunity to test some of these antibiotics. Most of the antibiotics that we are going to be testing either have that beta lactam ring where they're interfering with peptidoglycan synthesis, or they're those aminoglycosides where they're interfering with that protein synthesis. Now, one of the concerns with taking antimicrobial therapy or antibiotics has to do with side effects. So, we know that some can be pretty strong and can actually have toxic effects. So, this is when it's affecting that normal host tissue, especially the liver. So, some of those drugs that are used to treat tuberculosis can be pretty strong. So, usually people, have to check often to find out if their liver is able to handle it. Some drugs can also have some toxic effect against tissues. So I mentioned cellulitis. There were a couple of times that my husband ended up with cellulitis and ended up in the hospital. And the thing that seemed to work the most was vancomycin. And vancomycin is one of those things that can be dangerous to tissues. Not everybody can tolerate it because it can be painful. It's administered through an IV and it has to go through a very, very slow dose rate. So it can take hours to actually deliver the drug. And so he seemed to tolerate it very well, even though it was going very slowly. But they would actually move the port around because it would actually toughen the vessels and the tissue. So they would actually have to move the port around. We also know that some people can be allergic to antibiotics. This is when our immune system overreacts. So it's going above and beyond what it should be doing. And so this could be dangerous because if it's a type 1 allergy, it could actually result in anaphylactic shock. So I have a friend who took sulfa drugs and she broke out in hives and had a bad reaction. And so she called the doctor's office and they said, do not take another sulfa drug because it could be very dangerous. Now, some people sometimes mistake secondary side effects as, like headaches or upset stomach as being an allergy. And so for quite a while, they stopped prescribing penicillin because so many people were so allergic to it. And what they found when they actually did tests was that people were kind of mistaking those secondary side effects for an allergic reaction. Sometimes that can happen. Sometimes the person can have a really bad allergic reaction to it. And it's very important to avoid those drugs. Probably the biggest effect by taking antibiotics, especially if you are on a long course of antibiotics, is disrupting the normal microflora. So we have bacteria on us and in us. They outnumber our cells by like 3 to 1. A lot of this bacteria is really good because it helps to outcompete those bad pathogens. So if we take an antibiotic, we're not only getting rid of the pathogen that we want to get rid of, but we're also getting rid of all of that good microflora. So what happens in that case is that now there's space and resources for pathogens to move in. And this is when the person can end up with a super infection. So oftentimes, if people are on a long course of antibiotics, they're usually encouraged to take some pro and prebiotics just to replenish that normal microflora. So, the next thing that we will be talking about is resistance, because we know that resistance to antibiotics is a big concern. This is also a big concern when you're prescribing antibiotics as well.